Okay, in this problem, we're given a specified rate of change in current in a solenoid and some facts about the solenoid, and we're supposed to compute the electric field that's induced outside. So let's draw a top view. Here's a picture of our solenoid. Here's our observation point. Now we calculate the induced electric field. We're going to use a relationship that E dot dl along any closed path is equal to minus d phi b dt, the change in magnetic flux through the surface enclosed by that path. Now this problem has cylindrical symmetry, so the path that we're going to choose is a circle because that also has cylindrical symmetry. Therefore, we know that the E field has the same magnitude at any point on the circle because of the symmetry of the problem. We also know that E field has to point tangentially to the surface. We know this from Gauss's law. There's no charge contained inside the loop. And since there's no charge contained inside the loop, that says that Gauss's law says there can't be an electric flux through the loop. That means the E field can only point in the direction that's shown. In addition to the E field direction, we can define a dl direction at each point in the loop, and it turns out that dl and the E field always point in the same direction. This allows us to simplify the E dot dl integral using the symmetry in the problem. We know that the E field and dl point in the same direction. We also know that the E field is constant all the way around the loop, and therefore the integral E dot dl is 2 pi r times the E field, where r is the distance from the center of the solenoid to the edge of the loop, namely the distance from the center, 5.5 centimeters, where we want to find the E field. That's one part. We also have to compute the magnetic flux. Well, that's going to be equal to the magnetic field inside the solenoid times the flux through the overall loop. Now, the B field of the solenoid is contained within the solenoid. That means the flux through the path that we've drawn is going to be equal to the magnetic field times the area of the solenoid. It's not equal to the area of the loop because outside the solenoid, the B field is equal to 0. I can write down the expression for the magnetic field of the solenoid as mu naught times the number of turns times the current times the area of the solenoid, which is going to be pi rs squared, where rs is the radius of the solenoid. Okay, I need to calculate now the quantity d phi b dt. We're told that the current is increasing with time, so the number of turns per meter is not changing, the constant mu naught is not changing, and the radius of the solenoid is not changing. So that means taking the time derivative is straightforward. And I get a term out that's di dt. Combining these expressions, we can calculate the E field. The E field is going to be equal to minus mu naught n pi r solenoid squared di dt over 2 pi times r, well that's the observation distance. Okay, we can cancel out the pi's, and we can put in the numbers. We know mu naught's a constant, 4 pi times 10 to the minus 7 newtons second squared per coulomb squared. We know that the number of turns per meter is given as 892 per meter. The radius of the solenoid was given as 4 centimeters, or 0.04 meters. And the current change is 900 amps per second. All this is put over 2 times the observation distance, which was 5.5 centimeters, or 0.055 meters. Okay, we can multiply all these terms together to calculate the E field. What we find is that we get that the induced E field is minus 0.0146 newtons per coulomb. So the size of the E field induced is 0.0146 newtons per coulomb. And the direction is such, looking back at the diagram, since we defined the direction around the loop in the normal sense of the right-hand rule, it means that the E field actually points the other way.